kickstart, first and foremost, go into a little bit of an introduction. So first and foremost, obviously, thanks to everyone for joining us this evening for our sort of next episode of our Golang Live series. So I just wanted to give you a brief introduction to myself. So my name's Shaun Connor. I'm one of the directors and founders over here at Amicus Recruitment. And Amicus is sort of a niche agency who focus on recruiting for sort of Golang, Python and JavaScript professionals for companies based in the UK, the Netherlands and Germany. But given the world now, our candidate network is worldwide with what's happened over the past sort of 15, 16 months. So tonight we've obviously got our guest speaker is Patroklos. Patroklos is a principal engineer, and he's going to give us a talk tonight on discovering sort of Go's beauty of concurrency. So before obviously handing over to Patroklos, as always, these sessions are very interactive. So feel free to ask any questions throughout the webinar, and they'll be answered sort of in due course. So I'll just hand over now to Patroklos.
Yeah, thank you very much, Shaun. Thanks for the invitation. It's a pleasure to be here and talk about one of my favorite topics. So let me share my screen and we can get started. Just to give you a heads up, it's going to be like 3 different, let's say, topics. So by the end of each topic, we can have a short Q&A, and of course, at the end, we can have some more time so I can ask questions that you might have. So let me start sharing my screen and we can start the presentation. So like I said, my name is Patroklos Papapetrou. You can follow me on Twitter or you can find me on LinkedIn if we want to connect. I'm super happy to do that. A few things about myself. I worked for the last 6 years remotely for US companies. I have more than 25 years experience in software engineering. The last 4 years, my main programming language is Go. Father of 2 kids, and among others, I'm organizer of various tech events in my home country, Greece, like meetups or tech conferences. The topics for today's webinar, we're going to have some kind of theoretical background just to set the pace and the ground about what we're going to discuss in more details. We're going to explore Goroutines and weight groups in Go, then some Mutexes, channels, and like I said, at the end, we will have some time for a Q&A session. So let's get started. First of all, some essential theoretical background. Most of the time I get this question about what is the difference of between concurrency and parallelism. Let me give you a very quick, let's say, definition. Concurrency is, let's say, out of order execution of a sequence of instructions. It gives us actually the illusion that we are running multiple programs, multiple operations at the same time. And it's highly depending on the available hardware, on the number of CPU and the cores per CPU. Now, parallelism is actually when our hardware is running 2 or more instructions at the same time. Okay, there is no context switching between different programs, and we are taking advantage of all the hardware and we're running at the same time 2 or more instructions. Now, those things can be sometimes blended or they're sometimes completely the opposite. So today I'm going to show you how Golang's concurrency features support both, and we can run things concurrently or completely in parallel, depending on our hardware. One more thing that we need to be aware of is the Go scheduler. The Go scheduler is a tool provided by Go, apparently, and it's responsible to for 2 things. It's for orchestration of Go routines and synchronization. Just a quick idea of what those 2 mean. With orchestration, we mean the handling of interactions between 2 or more Go routines that run at any given time. And by synchronization, we mean the process of Go routines can have their turn to be processed. So the Go scheduler is responsible to decide which Go routine is the next one and which should be added to the next scheduling period. Now, about this scheduling period, let me explain a bit how the Go scheduler works. Imagine that we have a scheduling period of a specific time, like, I don't know, half a second or even less than 100 milliseconds. Now, if there is only one Go routine that runs at any given time, the Go scheduler will just assign that Go routine running through the whole scheduling period, which is 100 milliseconds. Now, if we have 2 Go routines, the scheduler will assign 50 milliseconds to the first Go routine, and then it will stop it, and then it will assign the next 50 seconds to the second Go routine. And if there have still more instructions to run, it's gonna do the same again until they are both over. Apparently, if we have 10 Go routines, the scheduler will give like 10 milliseconds to each Go routine. So this is like exactly what I say, the illusion of things are running at the same time. Now, one more thing that we need to keep in mind that, like I said, the parallelization and synchronization and concurrency rely on the hardware. So we need to have in mind that we have hardware threads, which is actually our CPU and our cores. We have operating system threads that usually run on specific hardware threads. And then we have Go routines we're going to see in a minute. Now, Go routines are usually always either a function or a method in Go. Like I said, they are running concurrently with other functions or other methods. You can think of them like really, really lightweight threads compared to an actual thread. If you're coming from a JVM programming language, they're really extremely cheaper than compared to them. They're using only a few kilobytes of the stack size. I mean, the stack can just grow and shrink depending on the needs of the application. If you compare it with a stack, with the threads in the stack, they have predefined size and it can be modified. Now, the Go routines are actually multiplexed to a few number of other OS threads, and this is managed by the Go Runtime. And we can have only a single thread program that can run thousands of Go routines, okay? And if by any reason, like a Go routine is blocked by user input, then the scheduler can move it to another thread, create a new thread in the operating system. All these are handled automatically by the Go runtime. So we don't need anything as programmers, as developers to know about that. All we need is to implement our logic on top of this implementation of Golang. So now that we cover this first theoretical, let's say, background, let's switch to our first live coding about Go routines. So I'm going to switch here context. Let me do this here. So let's see a very simple implementation of a Go routine. So I'm using the runtime package of Go to make sure that my program runs in a single thread environment. I don't want to use multiple cores at this time of the demo. I'm going to use it later on. And in my main function, what I'm doing is I'm creating, I'm initializing and running a Go routine using a literal unnamed function of Go. It's super simple, just prints a message inside the Go routine, and then I'm printing also a message in my main function. Let's run this program and see how it's gonna look like. So running it, you can see that we are getting only the message that is running in main Go thread, which means that this print message here is not printed out. Now, this is somewhat expected because our main function runs in a different Go routine, and we haven't told it to wait until the other Golang function is finished. Okay. Now I'm going to do a trick just to show you that it actually runs, which is not the correct way of doing things, and then we're going to do a more correct, let's say, implementation. Now, if I run again, you will see that we have a printed statement that the Go routine is running inside, and then we have something running in the main thread. Okay. Apparently, this is not the way to do things in Golang, but I just wanted to show you that how the two Go routines run concurrently, and we don't expect to see both of them if we don't use if we don't use the wait groups. So let's see another more detailed example. Okay, again, I'm going to use a single thread program here as a start. There are two very simple functions here. One that prints the English alphabet and another one that prints the Greek alphabet. Nothing special here, just to help us give some print output to explain the concurrency. Now, what I'm doing in this code here, I'm using the structure of wait group that's provided by the Golang sync package. I'm defining an empty wait group. And I'm using it's very simple. It has very simple API. What I'm saying to the wait group is that I'm going to use two Go routines, and I strongly recommend when you initialize a wait group, always use the add method with the exact number of Go routines that you know that you're going to run at any given time. Next, I'm creating a couple of Go routines, again, as a literal functions, unnamed functions. The first one is running the English alphabet. The second one runs the Greek alphabet. And in each Go routine, I'm using the done method of the wait group to indicate to the runtime that this function, this Go routine, has completed its execution, so we can consider it as done. Now, the last thing that I want to explain is that the wait method of the wait group is indicating to the main program to wait until all the other Go routines have completed their stuff, their execution. Okay, and then once this is both of them are finished, and it prints something like that. So let's run the program as it is, and then I'm going to do some. I'm going to remove some commands and see what would be the differences. So I'm switching back to the example, and if we run it, we're going to see that it prints the Greek alphabet and then it prints the English alphabet. Now, if you see, that's not the order that we have in our code. I mean, first we define the English alphabet and then the Greek alphabet, and that's exactly what I want to explain to you is that when we're using Go routines and concurrent, let's say, elements of execution, we don't guarantee the order of execution, but we guarantee that all of them will be executed, especially if we are running on a single thread program like this one. Now, I can run this thing again and again. Probably at some point we'll have the English alphabet run first, but it's completely random. It doesn't have any kind of consistency here, which one will run first and which one will run second. Okay, now let's do some modifications here so I can show you why all these three wait groups methods are important. First of all, let me change this to 1 and see what's going to happen. Now you see that the first, what it tells to Go runtime is that, well, you need to wait for one Go function to finish. And as soon as the first one is finished, then this function here tells the main program to exit. Again, it doesn't matter which one it will finish first. As long as it's only one, it will just end. So again, randomly, I think that at some point the English alphabet will show up here. But you can see that it's only printed only 1. Now let's bring it back to 2, and let's remove this line here and see what's going to happen. Again, I'm going to run my program, and oh, boom, deadlock. Well, that's quite expected. Let me explain why. Because as we inserted here, we said to the wait group, wait until 2 functions are completed. The first one is completed, but the second one is never indicating that it's done. So at some point, the wait group has an implementation to stop waiting and give us a message that, hey, I can't wait anymore, okay? All Goroutines are not finishing, so it's like a deadlock. So I'm panicking, I'm exiting the program. And let's see the last one. Let me remove the wait here and see what's going to happen again. Let's clear and run. Well, it doesn't wait, okay? The program just runs the Goroutines, and the main function, it doesn't wait about the execution. It just print the message. Those 2 will probably run in the background. It will not print anything because we have just exited the main function. Now, let's see again how what is the output of the normal flow, and then I'm going to change something to show you what's the difference of running things concurrently and things in parallel. Now I'm going to increase this number to 2. So in practice, I'm going to say the Go runtime to run things in parallel, meaning that, hey, I've got 2 cores, 2 CPUs on my hardware, so please run things in parallel. So let's see how this will affect our output. Yeah, you can see it's completely random. Okay, you can see mixed characters here and there, other Greek, other English. It's because now that we have 2 CPUs used, both functions are running exactly in parallel. There is no switching. Okay, there is no switching between the first Go routine and the second one, which are pretty super fast, right? So we are running both of them in parallel, and because they are printing things, we can see here that things are completely random. And again, you can see, things in a completely random order. English, Greek, it's completely random every single time. Okay, you can see it. It's pretty obvious. So while the first thing here, everything was running concurrently, which means that the 2 functions were actually switching context in our scheduler. When we're using 2 cores, they are running exactly in parallel. So let me show you something else about Goroutines. We have here another similar example, which is again 2 Goroutines. One is adding. We have a shared, let's say, variable here, counter. The one function is reading the value of the counter. It adds 1, and then it sets the value back to the counter. And the second function is reads the value, subtracts 1, and set the counter back to its value. Now, if we run this, since we are iterating 5 times, we expect that the output will be actually 0, okay? So let's do this. And if we run it, yeah, the value is 0, and we can run it as many times as we want. Let me do a trick here. Let me increase that to 1,000,000, okay? I guess we still expect that this should be, the counter value would be again 0, but it's not. And every time it's completely different, okay? Which it's totally unexpected, or not expected, I mean, unacceptable, because we don't expect our code to work like this. This is exactly the problem with the scheduling period. I mean, if you notice, the scheduler at some point will give, specific time for this Go routine to run, and maybe at some point, before the value is written back, the scheduler might stop this Go routine and might assign this one to work. So this Go routine will actually read the value, the shared value, without having this written. So we have like a completely data race and things go like crazy. Okay, I can demonstrate the same pretty simply. Okay, like adding a simple print function here, and you can see the same, because when we want to print something, the scheduler does breaks the function, does the operating system call, and then it resumes back. So how are we gonna fix this? There are actually two ways. The first one is to use the atomic packets that actually says the Go runtime to add or subtract things in an atomic way, actually run whatever has to be run as an addition, as an atomic operation. So let's run this thing, which is our other example here. Here we are. Yeah, and the result will be always 0 because we have used this atomic thing here. So it doesn't matter how many times we run, even if it will break, its function will be atomic, executable as an atomic operation. But what if we don't want only to add, and we want to have more sophisticated things like printing or logging something? Okay, and here comes the idea of mutexes. Let's go back to our presentation, or we can have some kind of questions for now. I don't know, Shaun, if there are any questions for this specific topic, or I can move to the next one.
I think there's one question, Patroklos, in the Q&A from Ravi, talking about does the Go scheduler schedule a Go routine automatically? I don't know if you can answer that.
Yes, we don't need to do anything about that. The Go scheduler, once we're using the Go instruction, it schedules the Go routines. Exactly.
Yeah, and then there's also a couple of other questions. One from Dimitri saying, what is the default value for Gomax procs?
Yeah, that's a very nice question. I can dive here and show you it is the default runtime number of CPUs of our current hardware. Okay.
Yeah. Perfect. And I think the final question, just outside this from Flavius, is not really related to Go routines, but what's the reason you've chosen Golang as your main language for the past 6 years?
Okay, I'm gonna answer that at the end of the webinar. Okay. It's a
okay,
nice question,
we'll come back to that one. Perfect.
Okay, cool. So now we've seen that we have a couple of ways to start data race. Let's talk about mutexes, which is actually the most sophisticated way of handling data races. So where is the presentation? Here it is. Mutexes, they are the locking orchestration mechanism provided by Go. Okay, their intention, like I said, is to eliminate data races. We have two flavors: the standard that actually locks everything. Okay, read and writes of specific value. Or we can have a more, let's say, advanced, which is read-write mutex. It allows reads, multiple readers, but it locks writers. Apparently, there is no free beer, okay? Mutexes come with some latency, especially the one with read-write locks. So we need to make sure that we are doing the bare minimum in terms of locking. I will explain what I mean. So we have the minimum latency to our programs. Now, let me go back to our examples about mutexes. I think it's the, yeah, this one. So it's the same example with addition and subtraction. Okay, nothing special here. The difference is that we are using a mutex. Okay, this is provided by, again, by the sync packets from Golang, and it's very simple interface. It has a lock and unlock method. So what we are doing and I strongly advise you to do so, is like, use this curly braces here to indicate which Go commands we want to include in that mutex. So in our case, I'm using the mutex to lock the execution of other Go routines until this Go routine has executed all three these operations, like reading the value, adding ++1, and writing the value. And again, I'm doing the same using the other function. To lock everything, I'm using the mutex.lock, and to unlock things, I'm using the mutex.unlock. Let's run this this thing. It's our fifth example, and again, yeah, it's running super fine, which is good. Now I want to show you something. If you notice the execution time, okay, it's mainly the same, about 35 milliseconds in my laptop, okay? But previously there were some, there's a variation, not huge variation. I mean, we're talking about milliseconds, but you can see that sometimes the previous example with the atomic operation was running, 30, 41, 45, blah, blah, blah. This is exactly the beauty of mutexes, because you can have like a more expected, time of running the Go routines. Now, let's see another example. Let me use the advanced, let's say, mutex, and see how this is working actually. So it's the read-write mutex, and instead we can use the read lock, okay? And we can use again, read lock, and then we can use read unlock and read unlock, okay? So let's run again our program. It runs fine, there is no problem, but look at the time. You see, it's almost 3 times slower than the previous one, okay? So that's why what I mean that any, advanced functionality that we can leverage in Go, like the advanced mutex, it's not for free. We have this latency because there is more, let's say, orchestration in the scheduler about which writer and which reader should be allowed to read and write this set variable. So if we don't really need that kind of things here, then I think it's super safe to use a default mutex, okay? And also, let me show you what is going to happen if I don't unlock things here. So for instance, if I forgot to unlock and I run my functions, I'm sure you already know what is going to happen. Yeah, okay. It's a runtime, a deadlock, okay. So one routine, Go routine, is actually not finishing at all. This one is not unlocking things. So the other one is just waiting before it, gets its turn to read things. So it's completely deadlocked. So again, we have this nice panic in our code base. So that's all about mutexes. So I'm going to switch back to our slides. Any questions about mutexes specifically?
I think there's one question so far, again from Ravi. He mentions if I start 2 Go routines in a function and one of them throws an error, is there a difference in error handling between this scenario and when there are no Go routines in the function?
Yeah, that's a little bit of advanced handling. I'm going to show you just after this slide about channels. If we need to handle errors inside Go routines, then the best way to do so is to do it with channels. And I'm going to explain how in a minute.
Okay, I've got a few more here actually. So a question from Flavius: doesn't the lock method negate the whole point of a Go routine?
No, to the opposite. I mean, we are now the lock method actually protects us from shared data, okay, from data races. Ideally, we wouldn't want that the Go routines are accessing share data. But if they have to do, we need to ensure somehow that they run their operations in an atomic way. So we need to use the log to make sure that at any given time, only one Go routine is reading or writing this specific data value.
Okay, we've got a few more. So question from Luke, what is the scope of the mutex? Does it apply to all Go routines across the whole program, or are they scoped to packages?
Well, it depends on how we use it. I mean, at this in this example, I'd use it in this file. Okay, so it's specific to this file. You can I would just use it in only in a package level or whatever. I strongly recommend to use the mutexes and all these sync, let's say, structures by Go. In the lowest granularity element. I mean, if you have something that runs in a specific file, limit down the mutex to the file. If you have things running on a package, then go to a package. But try to make it like really limited.
Okay, there's just 3 more. So is it considered bad practice to use mutexes instead of channels / rewriting logic to avoid locking, or it's fine in the same amounts?
Well, there's no bad or good practice. It depends on our case, right? If we don't have any data that we need to exchange between Go routines, then mutexes are super fine. They are the simplest way of orchestration. However, if we need to exchange data, as I'm going to show you in the next example, then mutexes are not enough because we need to have somehow to pass data between the Go routines so channels come to the rescue.
Okay, there's another couple still coming in. So any deadlocks caught in runtime from Carter? Carter asked that question. Are deadlocks caught in runtime?
Yes, absolutely. Yeah, but you can also do it on, you can, if you have tests, you can run the Go test with a deadlock parameter, so you can run data races during your test, and you don't have to wait until your program runs in, in production.
Okay, just 2 more. So, Marinos, can you define your own mutex locks for specific locking by specific processes?
Not sure if I completely understand the question. I assume defining our own structures of mutexes, or I haven't seen that done. I mean, these 2 kinds of mutexes cover apparently 99% of the case that we want to orchestrate Go routines. So I'm not sure if I completely understand this question.
Okay, and the last question is from Andre. So what is the best way to share a construct like configuration between Go routines, knowing that they may need to be changed, updated during runtime?
Yeah, if we need 2 or more Go routines to update a specific, let's say, structure or config, I think that's the best way. If we need to exchange values, send a value from one Go routine to another one without keeping it on a shared value, then these are the channels. But config, I think in the case of config, we need to do that using mutexes.
Okay, and I think there's just one final question just come in there on that last. Is there a reason to use channels for errors instead of sync.error group package?
So can you please repeat that, Shaun?
Is there a reason to use channels for errors instead of the sync.err group package?
Again, it depends on the context. I mean, Go provides 2 different ways of orchestration, so it depends on what is our business case. They have been defined for 2 different purposes. So it's unfair to compare those 2 if we don't have a concrete example. So it doesn't mean that something is better or worse. Again, it depends on what we need to achieve in our code base.
Okay. There is just one final one, Patroklos, before you move on.
Sure. Yeah,
so it's just from Harkamal. He said, what is the scope of mu.lock?
This one, the scope, it runs.
Yeah.
So if we dive into the code of this mutex, you will see that there's some kind of semaphores that once we run the mu lock, okay, all the others Go routines are using the same mutex They are just paused. They are just in a runnable state, not a running state. Only this Go routine is a running state. Once this part of the code finishes and we execute an unlock, okay, then that routine is removed from the runnable state in the mutex, and the next Go routine, which is randomly assigned by the scheduler, will run their own code. So the scope is like very limited, okay? Lock means that it will run only for this specific set of instructions.
Okay, perfect. Thanks so much. I think we're done for questions for that part.
Okay, let's see the last topic for today. I'm gonna switch my slides about channels, okay? Channels, which are, let's say, the most sophisticated way of orchestrating data between Go routines. Let me explain what channels, because some people are confusing channels. They are not any kind of data structure, okay? And they are not a queue, okay? So please don't confuse them with anything like that. They are super powerful primitives. They're language types, okay? But their main, let's say, goal is to allow signaling between Go routines, signaling of events. So one Go routine can say, I'm done with something, please get this information from me and do your own part, exchange information. So yeah, the very first question that we need to ask ourselves is, if we care about the guarantee that a Go routine sends a signal and this signal is actually received by the other Go routine. If we answer this question, then we can start implementing the right way. And that comes to the choice of buffered and unbuffered channels. A buffered channel, an unbuffered channel is actually guarantees that the signal has been received by the receiver, which was sent by the sender, Go routine, okay? The buffered channel doesn't guarantee that everything has been received by the receiver Go routines, okay? So the first thing to ask ourselves is, what are our case and what do we need to achieve to guarantee, and then we can use buffered or unbuffered channels. Channels can have 3 states. It's open when we just initialize a channel and has information, nil or 0 value that has nothing inside the channel, and closed when everything has been completed, then the channel cannot be used anymore. So let's dive into the some examples and see how we can use channels. So going back to our code, let's start by a very simple example here, okay? Let me explain what I'm doing. The first thing is to create a channel. Now, like I said, the channel has no data, there's no structure, so the only way that we can create a channel is to use the make keyword here, and then the keyword chan, and then defining the structure that we're gonna use with this, the data type we're gonna use with a specific channel. Now, this channel is unbuffered. If we want to make the buffer, we can just add the number of elements that we want to have at the same time in the channel. But in this specific example, I want an unbuffered channel because I want to guarantee that every single piece that I'm sending from the sender is actually received by the receiver Go routine. So let me briefly explain the code here. Again, I'm using an unnamed function, literal function that iterates from 1 to 10. And what it does, it sleeps for a random period of time, and then it sends some kind of message to the channel, okay? And then I have some kind of printout so we can, monitor the execution. On the other side, on the main thread, I have another, not Go routine, but another code. But what it does, it repeats constantly until there is nothing in the channel, okay, if not okay. It just breaks. But if there is something in the channel that can be read, then it just prints it out, okay? It's super simple. And like I told you, this is unbuffered channel, which means that every signal sent should be received before the next item in the channel can be sent by the sender. So let's run this example and see the output, which is going to explain to us. This is example 6. Yep. Here we go. As you can see, we are getting receiving, sending, receiving, sending. Now, if you notice, the output, the print element of receiving is before sending. And that's the beauty of this actual channel exchange. The channel is only ready to send when someone is available to receive. Okay, that's why we're seeing that the receiving is happening in quotes before sending. It's not like this is like we need someone to be there and accept the information that the sender is actually sending. So you can see that everything is like receiving, sending, and then sending is okay, signal is okay. Okay, so this is very important to have in mind. Now, this is a very common pattern when a function is waiting, a function is doing stuff, and it expects to have some information by a Go routine running in something else. Now, let's reverse our example and move, let's say, the sending outside of the Go routine, the main thread, and the receiving inside the main thread, the Go routine. That's the example here, as you can see it, okay? Now, it's very similar to the previous one, and the difference is that inside the Go routine, I'm receiving the signal, okay, and I'm sending it outside of the Go routine. This is actually the pattern that we call the wait for task, okay? The previous one was called wait for result. So our program is waiting for a result, the result of this Go routine, and it runs something whenever we have a result. And this example here waits for a task. So once we have something, okay, a new task from this execution, then we'll do something with this signal. It's the opposite way of doing things. This pattern here of concurrency using channels is actually used in more advanced concurrency patterns, which is like the pool mechanism, but we don't have time to cover all this today. But this is the idea of running things in concurrent. Let me run these things, this example, and see the outcome. It's more or less the same, okay? Again, I mean, there's nothing different. And the only reason, again, is that I have used a unbuffered channel. So again, the only guarantee that I have is that anything that is sent by this line here, 32, is going to be guaranteed that it's going to be received by this line here of my Go routine. And that's why you can see first that the receiving signal is printed before the sending, because like I told you, the channel here waits until there is a receiver to receive the signal that has been sent by the main program. Now, I want to show you a last example. I think we have some time. Yeah. So let's do this example about buffered channels. Okay. Now, assume that we have, this is called the fan out pattern, by the way. This is very useful when we know that we have a large amount of items to be processed, and we don't care about the order of executions. Like I told you, this is exactly the idea of concurrency. All we need to know is that at some point, all of them have been executed, and we don't care which one is going to be first and second, or vice versa. So what we do here is we are initializing our channel, our buffer channel, with the items that we want to process, 1,000 at this time, okay? And what we are doing here is we are iterating over those items, and we are creating 1,000 Go routines, okay? Not one, but we are creating 1,000 Go routines. Here, you can see them, okay? And each of those Go routines, once they are done, they're going to send their signal to the channel, okay? So 1,000 Go routines are going to send signals to the same channel. Now, on the main program, on the main Go routine, we are iterating as long as the items is more than 0, and we are receiving the value from the channel. We are subtracting 1 from the items to tell the system that we have processed this item, and then we are printing the signal to the output. Let's run this program and see what is going to show us. Here we are. So let me go up for a minute. Okay. So as you can see, items are the 1,000 Go routines are running in a completely random order. As you can see that each Go routine sends the signal to the channel, and this is the this should happen before, but just before the random execution of the Go routines is like the scheduler. We can see that the signal is completely random. At some point, you can see that the Go routines have been created, are sending signals, and at some point, our main program is starting to receiving signals without waiting for all the signals to be sent. So it receives the 4th, the 5th, blah, 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 but there are still signals to be sent, and at some point, again, it reads all of them, and as you can see, it reads them with the same order they are arriving. Okay, so that's why we're not reading the 1,000 element at the end. To show you this in a more, let's say, in a better way, I can add a sleep here. And again, please don't use that in production. This is just for a demonstration purposes only. So I'm adding a sleep of random seconds. So that means that our processing, okay, the creation of the Goroutines will be slower. So we will be able to see all this interaction in a nicer way. So you can see that, the Goroutines slightly they are starting to sending signals, but okay, we don't receive anything because we need to wait for all these 4 loops to finish. Okay, so it won't start to process because not all of the 1,000 Go routines have been created and processed. Okay, so let me do another final change here. So I'm gonna create all the Go routines, okay, but I'm putting the sleep inside the Go function. Let's see how our output will look like. Randomly, you can see again that things are sent super fast, okay? And our system reads things without waiting. So what I show you here, there are multiple ways of using the Go routines and the channels. Again, this is a very, let's say, not scratching only the surface, but we have dived into some examples, some concurrency patterns, but there are lots of stuff to explore in channels especially. There are lots of patterns, but we don't have time to explore all of them. So I'm gonna start the presentation now, and if we have any questions, I can take them now and we can discuss it.
I think there was one during that. It was how do channels differ from queues?
They are not queues, actually. The queue is like first in, first out. But like I told you, we can, like we said in this example, okay, let me remove that again and run it and see the output. So we are adding items here, okay, randomly, and the reader, again, reads them randomly. There is no order, there's no first in, first out in the queue, okay? So items are added randomly channel, and the receiver is reading them again randomly. So it's completely different than a queue.
Okay, perfect. I think there's a question, what are the benefits of using channels instead of wait groups?
Yeah, as I explained, there are no, you can exchange data with channels, pass data from one goroutine to another. Wait groups cannot do that. They are just locking the execution. They are wait groups is a synchronization method of the Go scheduler, and channels they are orchestration method. If we need to pass data from one to another, we should be using channels.
Okay, so a couple more questions. What are the best practices to handle errors inside Goroutines?
Again, we should have a channel again for errors, like error channel. So we can have this thing here, should be like error, okay? And then we can feed this channel with any kind of error. And at the end of the Go routines, we can start iterating the channel, the error channel, and to see if there are any errors, collect them, and depending on the business logic of our application, we should do something like return a multi-error or print an error or something. But handling errors is exactly the same. It's like we are passing data from one Go routine to another. And in our case, the other Go routine is our main Go routine, okay, here. So we want to pass something from 1,000 Go routines, like data or error, to the main. So we need a channel of errors to help the Go routine, the main one, to decide how we're going to handle that.
Perfect. Is there any advice on how to test parallel execution?
Well, that's a very, let's say, pain in the ass topic, because, like I said, it relies on hardware. So if you test something on your machine that has, I don't know, 8 cores, you can play around with this thing here and do stuff. But when you, let's say, run your unit test on a Docker image, on some Jenkins slave, or on the cloud, you might not have the same, let's say, hardware. So you might end up with different results, okay? So I don't think that is a silver bullet here. I would say try to run all your tests using only one core, and make sure that your program runs concurrently in one core, and you have more than even better. I mean, parallelization is always fine.
I think there was one from earlier. It's not related to Go routines, but why did you choose Go as your main language? Yeah, I think we'll just wait on that one.
Yeah, so I think that Go has all the benefits of a high-level language. I mean, it's not like writing C or assembly or anything like low-level, but at the same time, it gives you so much power of actually writing programs and code that interacts perfectly with the operating system and the hardware, like we've seen here. So you have all the power and the flexibility. It has a very small set of instructions, super easy to use. It has great support of the community. It's a very powerful and, let's say, minimum of, in terms of instructions, language.
Okay, perfect. I think there's another question saying, where do you apply parallel execution?
Like I said, because we don't know where our systems will run. If we know that our system will run on machines that support parallel execution, and our code is not affected by concurrent and parallel, like we've seen the example of printing things out, okay, then in that case, if we made our code completely independent of concurrent or parallel execution, then we can leverage the parallel execution of the hardware. But we should make our code work both for concurrent or parallel execution.
Perfect. There's one more question from Ravi. So going back to mutexes, what is the use case of using different mutex variables across Goroutines instead of using the same mutex variable?
Well, if you are using different mutexes across Goroutines, then any single mutex can handle a set of Goroutines. So they are in a completely different, let's say, context. They don't have any relation between them. So they can, if they share the same data and they are using different mutexes, then we have data races again. It's like using no mutexes at all.
Okay, and I think Ravi is in the same question. Also, if a variable has done a mutex.lock in one Go routine, can it be used to lock another resource in another Go routine?
I haven't done it, but I think so. You can do that, I think.
Yeah. Okay. Is there any more questions from anyone? Obviously, final questions. You just ask if there's any final questions from anyone. Usually give like 10 seconds to get questions in. It doesn't look like there's any final questions, Patroklos. So I wanted to obviously say thanks very much to obviously Patroklos for the excellent talk. There's obviously some really good ideas that you've given to the audience around your topic, and thanks everyone for joining and asking a number of questions. They were answered brilliantly by Patroklos. So just finally for me, the webinar is all recorded. It'll be posted on our YouTube channel, and I'll send an email out to all attendees tomorrow. If you obviously want to have any further questions, Patroklos has kindly said that you can all connect with him on LinkedIn, ask him any questions you like outside of this. And finally, for myself, obviously, we do many Golang talks. If anyone's interested in ever speaking at one of our Golang live events or wants to listen in the future, please obviously either connect with myself or follow Amicus Recruitment's LinkedIn page, and you get all notifications about upcoming events. But yeah, once again, just want to say really big thanks to Patroklos really for the excellent talk.
Thank you so much. It was my pleasure. I hope people learned something, and they're going to explore more about concurrency in Go, which is a super useful and fascinating topic.
Perfect. So yeah, once again, thanks so much everyone for listening. Have a great Thursday evening or morning or wherever you are joining across the world. So, and hope to speak to you all soon.
Yeah. See ya. Bye bye.
Cheers.